Yeah, all right, guys. So this is the kind of webinar that I have put together, trying to give you a kind of flavor of what is this well-designed all about and how to actually be on the top of your game. Because everybody have seen a lot of designs in their lifetime, and to build a proper design is actually quite a kind of challenging topic. And you just have to remember that you are an engineer. Whenever you are tasked to do something, you have to come out of it with strength and something that is empowering for yourself and also your team. So that is the kind of philosophy that I have seen successful well designer always follow. I used to work in various big companies offices where people would not let go the design until they have seen it with all improvement and all strengths of their experience is built into the software, in this kind of work that they put together. So the modeling is actually their expression of their experience, and that kind of well-designed approach is the superior approach that actually is very powerful. So I'm going to switch it to the slide mode if you give me 1 second, and maybe get ourselves a pointer as well. So this is something that is important for anyone to know and appreciate. What is a good well design? If you know what that is, then the first thing you do is to think about building it yourself. And then once you have built it, you are happy with the build, you have to go about optimizing it. And optimizing it for two things. One is the design of this well to be strong so that it's easy to understood by anyone who is using this design. And second part is it facilitates the execution when it comes to well construction, which you want to call drilling and completion, is actually easy to implement and cost effective and everything. So I will not hold too much on this point basically, but you will see a lot of little tips here and there, and we will talk through them. Okay. So the agenda for this course is the introduction about the kind of webinar, which we'll talk about the well design a lot, and introduction about myself as well, which and Akhil has already done. So I am going to skip the slide. Well-designed goalpost. What is the kind of goalpost that you need to follow? What is the scope of this design? This is the most important question. When a design comes to you for solution or you want to build a design, think about the scope. What this well-design needs to achieve to be successful. Goalpost. And then you say, okay, I have built this. Can I de-risk? There had been few issues with a lot of wells. You need to just think about the risk that your future well is going to see or encounter. So it's an important thing not to just to go blindly designing things when you should know the ground realities. You need to know the ground realities because your design have to face it when it comes to well construction. So it's a very important thing to make your design a little bit de-risking your wells. Otherwise, you just have picture something, draw a cartoon character, basically. So it is not good enough. So you need to build the design and then de-risk it. Against what? Against the realities, against the harsh challenges of drilling. And we'll talk about life cycle of the design. Everything has a life cycle. People, things, designs, projects. So I would like to say that well design has got a life cycle where you need to let it grow, let it solve, and then improve it. You have to improve the design as you go. Otherwise, you did something and it did not work as expected, and you said, okay, goodbye. You want to improve the design and use the design actually. Once you improve it, you can use it even for drilling execution. You can use the same well design. If you have been following it, you can empowering yourself with calibration and solving real-time drilling optimization problem. So the well design is not just a one stop. It's a life cycle. If you go it this way, it progresses with the project. And then you have to also remember the best practices that a lot of people follow around the world. what are the best practices that you need to adhere to or think about using them. So we will talk some of those, and we will also have some example for ourselves to think about some of the things that we can do even without using any software sometime. Okay. Uh, then at the end of this short webinar, we will be interactively reviewing some of the complex well. For example, there is a simple ERD well, extended reach drilling well. I'm calling it simple because it looks very simple to me compared to the most difficult well we have drilled. And technically speaking, your kind of departure from your origin of the well, if it is 2 times of your TVD, this is ERD. In this particular example, you are only 1.5 times more. Suppose the TVD is 10,000, it's only 15,000 out, stretching out to 15,000 feet. So it's a very nice interaction about the software, because the software itself is a machine. And in order to work with the machine, you need to be join it, properly understand it, and then it's not modeling that we are after. We are not after modeling. We are after problem solving at the end. Of course, we will have some question and comments. We will leave 10-15 minutes at the end, hopefully soon. Then we would like to answer any of the questions that you guys have. Okay. So looking at it, introducing myself, as we say, I think I would like to also say that teaching is not something that I have done a lot, but more recently I've been doing a lot of teaching in the universities. I've been teaching in the University of Leuven for last 4 years, 5 years, and working with very, very qualified PhD professors, including the chairman of the department. Basically, I share courses with them because of the level of expertise I have for problem solving. I may not be as qualified as a PhD or something, but I bring realities from the drilling field and operations. We solve bigger problem. If you leverage the data and your knowledge with the modeling and simulation, you can actually solve huge problems. So I think I bring this. That's the reason why they still have me for some time for this MSc courses that I'm teaching. And I'm still teaching these courses for this winter semester that these guys are doing. So it's kind of very kind of good appreciation from a lot of people, which I really can appreciate their understanding and kind of something that I can bring to the table for any of the course that I like to teach, because this is the whole idea of teaching. You need to share the knowledge and let these people run with the knowledge. And that's why Nikhil and myself have brought in softwares, because without software, we are talking in the air. We are not talking in the real problem solving, and modeling and simulation cannot be done without the environment. So that's the whole idea of bringing this in for our this diploma course, which Nikhil has referred early in this presentation. So I think we'll just maybe go to the next one. Well-designed main consideration. The main consideration is the goalpost, what actually we are trying to solve. You need to design the well in the way, design, drill, and complete, which is the whole construction, basically. Before that, you will do the designing and well planning, and then you run with it and drill it and construct it and complete it with the completions and everything in the way that actually maximize the returns, maximize the production, maximize people's investment. Everybody will be happy. However, in doing all that, you need to make sure that environment is not damaged and the risks are minimized. Operational risks to the rig, to the people, HSNE, and all kind of bad stuff should not happen. But that's like you want to win everything and you don't want to lose anything. So for me, the most important part is minimizing the risk and environmental impact. Think about, you have done a good job with everything. Let me just stop it for a minute so I can talk through. Think about this, that you have designed the well, fine, no problem. And then you also have drilled it without any incidents. And then you have completed it in a way that was very fast. However, it did not deliver too much oil and gas. That's not your fault, basically, because you designed it well. You did a good job as a drilling and wells engineer. Somebody gave you the wrong targets to drill. Okay, so you may be in the wrong place. So This is not your fault, but a lot of time bad things happen when people rush it. Environmental impact is one of them. They can shut down the big companies. Think about Mokando well. Everything was fine with that. People were pushing to rush to complete and finish drilling. There were signs of trouble. People did not bother because they wanted to get it done. And working on offshore rigs, I used to work offshore for 7 years. I really love the environment. People yell and scream as much as they like. Nobody gets upset. That kind of harsh environment I used to work. What I find is bad is people rush each other because they know the rig is costing so much money. The boss will be very unhappy. I would like you guys to be aware of these push and pull mentalities. Don't rush your designs, because if you have a bad design, you may not get to the oil. You may have suboptimal production. At the end of the day, you will have problem. Somebody will come ask this question. I have seen this so many times that people rush through things. In our business, we need to slow down. And when it comes to well design, I believe it still applies. Well design is building a blueprint. If you build a correct blueprint, you will have a correct building, the perfect construction, the very good construction. If you don't build a good blueprint, what you're gonna get, you will get what you have drawn and built in the design phase. So design it right, and then there you go, and you have done a good foundation for your well. Then rest of the things will nicely follow if you keep your eyes on the things and follow along. That would be the kind of philosophy that I would like to follow. And of course, you have to achieve all the subsurface objective. When I say all, it should not be all of them, because if you come to subsurface team, they will give you a long list of the objectives. For example, they will give you the BOD, basis of design, and say, okay, guys, the drilling people, wells people, here is my list of the things I would like you to deliver. Deliver me this well in that shape, and this will be my completion. This will be my targets. And there you go. There's a kind of, handover list of the KPIs, basically for you as a design engineer to implement and construct a picture around it. But not all of them are critical. If you want to please them with all the bullet points already matched nicely, your wells are going to be very expensive, very likely to be very expensive. You need to write down what is most critical for these gentlemen and these ladies in the subsurface department, and make a list in the hierarchy of 1, 2, 3 in the importance list, and then put another box underneath that should say nice to have. What are the nice to have these guys will be okay with? What they definitely need is the most important thing that you need to focus on, because if you ask them, generally speaking, since subsurface team is not drilling people, they are not drilling people, they may ask for things that will cost you a lot of money if you implement it. You can ask for flexibility. You can ask which ones are mandatory, which one you can change just a little bit. For example, a target. They have given you surface location. Maybe they don't have to give you surface location. You give them surface location. That is best for making the well cheaper. I used to work as a well planner for very big operators. They just say, okay, these are the targets, guys. This is what I want to reach. I have few options on my surface location. You will tell me which location is best for me. That's the way to approach it. But sometimes they will give you surface location. This is the surface location. Sometimes it's fixed, but you don't have to assume anything. That's just a very important thing to remember as a well-designed engineer. Ask questions, sit down with them. But traditionally in oil and gas, people want to keep them separate. Even they are not in the same department, even same floor. In the Middle East, I know there is a big company I know of. I was asking if we can speak to some subsurface guys. They told me they are at different floor deliberately, because they don't want them to be talking to the drilling people too much. So this is the kind of cultural thing, basically. But with smartness and the data-driven stuff, people know it's a very silly exercise not to collaborate as much as you should be. Okay, so coming to well integrity and safety, if your well integrity is bad, You just finished drilling, you tested the well, everybody is dancing and very happy with the production tests. And next thing you know, you start to have well integrity problems, like the pressures are showing up in the annulus, some bad stuff, and very, very, very bad stuff. Something I have seen in my time, we finished drilling the wells. As soon as we finished the drill, we did the test. The production was through the roof. People say the well came like train. It was as fast as a train. The production was great, and the mother nature was helping. But there were some signs of some gas migration, and that showed up in the annulus. And then somebody say, oh, okay, we wanted to save some costs, so we did not put gas tight cements. We used these cements, and that was cheaper. That was available right here. That was the source of the problem. So those things actually can bite back. I've seen it a few times, and I don't want to see it again, but unfortunately, people want it to be kind of faster and quicker. They need to be smarter. They could be faster if they like to be, but first they need to be smarter with what are the repercussions. Try to avoid complexity in oil and gas. Well construction, drilling, and completion is a nasty mix. People don't want to be complex with the things that may or may not work properly. It may or may not work. Maybe it works. Maybe there's a 10% chance it will not work. If it's a 90% chance, you want to go there. So avoidance of complexity is one. Sometimes you cannot avoid complexity. If you have an ERD well with underbalanced drilling going, this is complexity. However, you need to break it down into simpler steps. Even making a trip is hard, making connection is hard. They have to follow certain guidelines, a lot of things, but people have get it right. At the end, after doing it for last 100 years of these, people like to play with it. People say, okay, complexity, let me make a kind of long list of the things that I will do this way and that way. It has worked before, it will work. But see if you can avoid it, that's better. So focus on what is required. Like I said in the first point, you need to have a collaborative discussions with what is required and what is not required. In this business, you start drilling the wells, people say, okay, this well I want to drill, the next well should have this, next well should have that. And some of it is just nice to have. It does not bring any monies. It did not improve any performance. So you need to separate them and make sure that you do not miss what is required to start with. And also what is nice to have. Nice to have, there are a million things. If you come to a service company, you ask the service company, Mr. Service company guy, tell me this, I plan to drill these wells, what do I need? They will just give you the whole brochure in your hand. They say, okay, this is everything that is in here, you actually need it. And this is something that I learned myself that people do. So the only way who can defend these things, yourself actually. If you're working for the company in question and you're dealing with these gentlemen who are trying to sell everything, you need to push back. And you need to do the design work. The well design is your tool for finding the truth. A lot of time you are just finding the truth. You are seeing issues with the whole cleaning, for example, cuttings are not getting to surface. You want to find the truth. If you call any experienced drilling engineer, he will tell you, oh, actually, this is the RPM. We have very low RPM. Let's increase the RPM and the flow. That's the wrong way to approach it. Yes, of course, you can try it if you want to be at sleep. Then you can just follow these guidelines which somebody said to you. How about doing a modeling of status quo, replicate this in the well design and find out what the current parameters should be. Are you lagging behind in that? So those kind of things, you use it for well design. This is your idea to use the well design, not only for simulation, but problem solving, really. Okay. So well cost effectiveness, if you do not keep tabs on drilling, if you're drilling the well, constructing the well, you already have the plan and the design. You think about your design, it needs to be implemented. Would you like to make it easy for drilling or would you like to make it hard for drilling? Hard for drilling means they will struggle to make it happen. Suppose in the top hole, you decided to use maybe a mud motor, and there is an rotary steerable tool that you could have picked up that could make the ROP very fast, and the wellbore quality could be faster. Maybe you need to choose the right thing for your design. Design your valve for RSS. How would you design it for RSS? How would you design it for a mud motor? For the mud motor, you can have high dog legs. You can afford to have high dog legs, but you cannot afford to have high dog legs for top hole in the RSS. So you may need to design the well according to your requirement. And lastly, I want to mention these well longevity, which is like a lifespan of the well. Remember, you are drilling for 2 months or so. After that, what will happen? Everything will be taken over by the other team, the production team and the operating team. They will be producing out of it. Is your well good to go for 25 years or 30 years? Is the well you constructed, is it good to go? Or have you left some gaps that will bite back and the well production will be compromised in few years' time? A lot of wells fail in the first 5 years. When they start to produce, the downhole architecture starts to fail because somebody did not design it correctly or the way that they had been operated on. Production need also to match. You cannot do aggressive production on the equipment that are not designed for it. You need to design in harmony of what you are going to produce and how fast and everything. There is a separate discipline for it. On your part, I would like to suggest that you sit down with subsurface team, maybe a senior petroleum engineer, reservoir engineer, show them what you have designed it for so that it is in sync with what they were expecting, how they are going to use it, so that you can upgrade or downgrade equipment according to the requirement. That way you guys will be in sync with each other. So well longevity, which is the kind of mantra. Let me share some story. There was a company, they are national oil company in the Middle East. They come to London for interviews. One of my friend went to the interviews. He was a completions engineer. He asked a question with them, asking why they come here to London in the UK to get a completion engineer. And they very shy about it, but he insisted to know why. Then he was told that they drill like 10, 15 wells in a campaign. Everything was very, very cost effective and cheap. They were quite a big saving compared to the old ways they were doing these wells. And later on, 60% of those wells have well integrity problem, completion related issues. So that's why they lost a lot of money, because those wells were offshore wells, 30 million each. 30 million times 10, do the math, 300 million. 60% of them are unproducible. They are not able to produce. Why they are here? Because the well longevity was not looked after. It was drilled nicely, complete and tested. It did not last. That was the very hefty price that these guys had to pay for. So just kind of reinforce a little, guidelines about this is the most important part that design should hold. Let's talk about the kind of process. When you are at the starting phase, you are looking at conceptual designs. You may, if you are a design engineer, you are thinking about the future campaign of drilling. You will think about, okay, I have few ideas. Maybe this well, this way, these shapes of the well, these are the casings that I want to put in. You get few options, different option. They should not be exactly the same, of course. Different option, different number of well combinations, different type of maybe completion if you want to try different options. So you have few options. And also you think about, if the most complex option you are considering, what kind of rig you are going to need. Just a rough classification. And the site, the surface location that might be suitable. If you're going for ERD well, for example, you can have a site here to get to your target. Or maybe I don't have to drill ERD. Maybe I will go a vertical well on the top of the reservoir. That way I don't have to spend double or triple the monies. So you can also do all these exercise. Rig selection is the most important part. What kind of rig? Can it handle everything you might be using, or you may decide to change your plans later? So you have to think about the rigs, specification of the rigs, then classify the rigs, identify the sites that you might be considering using. So you have the option in the sites and the rigs. You also have now options and the kind of variants of your well design. And there you go. And next one is you say, okay, I have gone through all the design. I presented it to my guys and the subsurface teams are happy with one particular design. You said, okay, that's fine. Particular design. And after that, you say, okay, I will make it a proper picture of my design. I just selected it. Now I have to dig deeper. In the detailed design phase, you will look through everything that is on it so that it becomes like an open book. And you can read through everything. There are no uncertainty that this design that you selected was wrong or maybe have some flaws. How about if you find flaws? You go back to your conceptual well design. In the ideal world, you have to say, okay, let's pick up some other design. Let's find some other design. So you don't go with it if you find too many gaps. When you try to fix the gaps, it did not get fixed. There are constraints you cannot surmount. What are you going to do? Of course, you have to pick up a different design, but you don't want to do it in a rush because you have to follow the procedure again, go through all the checks and balances, come back to your detailed well design that made sense. At this point, when you finish this detailed well design, you are master of your well at that point. If somebody had any question, you may be able to answer it. At this point, you will feed it into the drilling program, and drilling program is implemented. And when I say implemented, you construct the whole well architecture. Okay. And when you constructed it, you still use the design, by the way. The design you had, a detailed well design, now it is a live design. It is infused with real-time data. The real-time data is making it powerful and a problem solver. This is called real-time drilling optimization, which is something that I have done it in a real-time center setting. A lot of real-time centers I used to work in, I found my designs to be working and problem solving. So those design has a certain journey, as you can see. It's a live thing. It gives you the fruit all the way of optimization. Every step of the way, you have benefits out of it. If you want to be critical and critical of your design, make sure it grows and it improves, it solves, and it matches with realities, which is the real-time drilling optimization. Okay. And I would like to just say, draw a line here. On my left-hand side, you have a lot of design. On my right-hand side, you have more of execution. You will do the design to check on the things and keep it on the track. However, you are totally focused on executing the plan. If you are on the rig, if you are an offshore, let's say semi-submersible rig, $750,000 for each day, $500,000 or something like that. I have been on the rig which was $1.5 million a day. You don't want to just say the designs are this and stop drilling and let's focus on something else. We need to follow the motion and try to complete it as soon as possible so that you don't miss out and lose any money. But you don't want any failures. If you have any issues with the hull cleaning, you don't want them to get stuck. That's where the modeling comes in. Modeling will tell you if they are going to get stuck. Is there any problem that is start to show its face? And before you know it, they got stuck, or they need to do extra wiper trip, they have twist off, they have lost the BHA in the hole, all kind of bad things, but there are always signs. Just like anything in the world, there are always causes, subtle things, subtle changes. Your real-time modeling can tell you this. You will see the deviation from it. So this is very powerful. On my right-hand side, all about designs, but in the real-time mode. On my left-hand side, you have design and design and designs. Okay. So one more kind of very busy slide. Sorry about very busy slide. What it is telling you is de-risking the wells in the design phase. What it do to the actual well? You actually plug the holes. If you have any gaps in some of the wells that needs designing, if you do a good job with improvement in the design, try to replicate the previous failure. Whatever have failed in the past, you want to fix it retrospectively, looking back over your shoulder. For example, let me give you an example. If few of the wells had a stuck pipe, and you find out that, okay, this problem, when I had this problem, it cost me extra few $1 million. What should I do to fix it for my design phase for the next well? Of course, you will open up everything about the data. You will replicate the stuck pipe using the digital drilling expertise and plug this into your designs and solve the problem that way. It's very interesting and very powerful, basically, this way, that you can solve the problem by looking back, recreating the problem first. Then you know what triggered it. Maybe the directional driller was not moving the cuttings because he was sliding too much. He needs to rotate more, or the shape of the well was not correct. You can change the trajectory to see if that actually corrects the problem. So it's a huge lot of things you can do, plug the holes so you don't get to see the issue through it. And also for when you are drilling, you also do the analysis, which I just told you about. So I will keep moving to the next slide, because this is the big slide, which is telling you you can actually fix the problem before it happened. This is your job as a design engineer, to fix the design in the way that you don't get to see the problem, but you don't have any crystal ball. You have to pull all the data into your well design, calibrate the design, recreate the event that had happened in similar wells. And then you have a clear picture of what you need to do differently. Then you solve it in the design yourself. Okay, the best practices, clarity. Of course, I mentioned about clarity of the drilling objectives. When you say clarity with the subsurface team, clarity with your drilling operations team, clarity with your bosses. No one should be falling out of it that I did not know this, I did not know that. And those are actually come very handy when you do the presentation. People are aware what you have done and why you have done this way. So clarity of this object. And secondly, you will build the well and the design of the well according to what is the objective about. What are the objectives? Are you meeting those objectives? You have it on the piece of paper. When you finish your design, you should be able to tick them off if you are doing your job right. So it's a kind of very common sense thing, actually. Okay, so inputs of your design, if you have wrong inputs, you will get wrong outputs. That's a common sense again. Validate your designs, calibrate them with, you don't have real-time data a lot of time. You may have to use offset data. And when it comes to drilling, you can test it with real stuff, which is real-time drilling optimization. However, you can calibrate it with similar wells, similar section, similar kind of operation. For example, if I want to run completion in the future well, I will see how was the friction factor was like. Can I calibrate it with similar operation? So I can calibrate it and validate it in that way as well. Peer review, if you have senior engineers, when I say senior, it does not mean the oldest guy in the building. It could be the, some engineer who has done it before yourself with various companies. So that could be the peer review you may want to use. A lot of people in oil and gas, they are not like, they are not like very collaborative in the sense that if they have done the design, spend 2 years or very long time, they don't want to share it with you. They don't want anyone opinion because they got their confidence on that design. I have seen this actually, and I will tell you one example in this presentation where I have encountered with a situation like this where somebody with 40-year experience, 40-year experience had done a design that he could not defend. He did not get it peer reviewed because he was so experienced, people believed in him. But when he went outside, people like myself had a chat with us. And in 10 minutes time, we were able to find things that he did not investigate. And that's not against him. It's just a technical matter. I have no personal interest to break other people's designs or prove them wrong. I did not say that he was wrong. I just told him, did you investigate these areas of concerns or challenges? Answer was no. So I think there was a need for, so peer review can help you bringing in outside improvement, because yourself, you cannot improve up to certain limit, you cannot improve because this is your experience. You need to get other people's experience to improve it from different dimension. Okay. Okay, so continuous improvement, of course, the design can be continuously improving. For example, think about this, that somebody use MPD, and MPD is a 10% of the well cost, hugely expensive technology. And when they finish MPD stuff and the well was finished, somebody say it worked fine, it did not have any problem. And you as an engineer, if you are the design engineer and ambitious and focused, you say, no, I want to see if the design needs improvement. Can we look at, do we actually need MPD? Because now I have the data of MPD and the drilling window is in front of me now because of using this special technology. I know if I can check on the drilling window. Do I have a drilling window without MPD, or do we still continue to use it? And that's something that actually materialized in one of my project. We were using MPD every time. And at one time, because I was new to that area, so I asked that question, why are we using MPD continuously? It costs 10% of the well cost. The gentleman say, if you don't like it, why don't you find out? So I draw all the data and plotted everything, and we find out that they actually did not need MPD. There was a drilling window, and we did a study on it. Actually, we said, okay, it's so critical, we don't believe what Naeem says, let's bring in a third party to prove it. We brought in third party, told them the story, give them the data. They also come up with the same conclusion, because it's not rocket science. Anybody with the correct state of mind can actually see the drilling window. So those kind of things are continuous improvement. Even though nothing failed, you have to think about continuous improvement. Further tips, there are enough of the tips. I think I need to probably take you to the software where we can actually do some optimization interactively, but let's just finish this in next couple of clicks. Choose the right rig, drill the right well from a right location. It's a very strange way to say that, but if you don't have the correct rig, you will be struggling to drill them. You will running into the risk that you have never thought about. And you can hear about a lot of things in the geothermal domain right now. They use very, very small rigs. They are drilling for 1 year, almost 1.5 years, 2 years. They're drilling single well because the rig keep failing. Rigs are doing all the stuff. So there's a very big lesson learned about these things. And drilling the right well, you're supposed to be drilling, for example, a slant well, and you came up with an ERD well when you do not really need it. It may be okay for drilling a slant well. If you do the modeling in the subsurface domain, if somebody missed something, somebody did a mistake, they will tell you to drill ERD well. Actually, if you, I mean, it is something that is also important to know, that you need to find out if you're drilling the correct shape of the well. Do you need to have ERD well, or maybe 2 vertical rather than 1 ERD, or 2 horizontal compared to maybe 1 ERD? So it's kind of something that is not done by yourself. It should be done by the subsurface team. But so it is very hard to actually find out, but you have to implement it. So you can ask this question to see what combination of the wells are best. From a right location, what is the optimum location on surface? If you have the wrong location, your wells are going to be longer and turning and twisting. When they are turning and twisting, they will be very hard to implement. It's a one big thing. If you get it wrong, if you have a wrong surface location for a deviated well, you will be paying a lot of money for no reason, basically, because you have to turn, twist, drop, get to the target somehow. You need to bring the location, whatever is the easiest to drill to get to your targets without making the well so complex that it will cost so much money. Because a well is complex, it costs money, very straight, and the risk goes up as well. Well trajectory, kickoff, dog legs, and everything that you need to get them right. And the casing wear, people say the contact forces. Most people don't have casing wear software, so they say, give me the contact forces. So contact forces are the indicator for that one. If you have high contact forces, when I say high, there is a number on it, which we need to watch for. And we can multiply and estimate the casing wear if you don't have fancy software. I use the fancy software worth the time. Sometimes the casing wear can eat up the very nice casing structures. Drilling fluid, mud weight management, rheological properties, all the things are, drilling fluid are the most important thing because they are the median that transport the cutting, give you everything that you need to get to the target. So it's a very important recipe. 2,000 barrels of it, 2,000 barrels, the whole is filled with mud, this drilling fluid, very complex. Its properties are not even normal. It's got different tables, sometimes different shape. To maintain it is a big task. Designs of the BHA, including the bits, downhole tool. Most important is the drill pipe. If you get the wrong drill pipe, everything will be hard. And I will take you to, okay, just a kind of now getting to the ease up mode because we need to show you some of the things in the design. So well designed, when to stop and think. When something is looking too complex, it's time to think about it, that why it has become so complex. Is there a need to be complex? So I will probably maybe stop it here because we will run out of time otherwise. I will probably wanted to show you some of the examples, but I think the examples are okay because they are just showing that how people have found the problem. But let me take you to actually interactive session. If you give me 1 second, let me get connected to the internet here. Okay, guys, so let's go interactive. We will be looking at ERD well. The ERD well is extended reach. It's not a proper ERD because it's a shorter kind of reach well, but it will have certain challenges which you will find out soon enough. Okay, so I'm going to share screen one more time. So if you give me 1 second. Okay. Hang on a second. Okay. So can you see my screen at the moment? Yes or no? So this is the kind of shape of the well. And if you look at it in the design phase, if you're a design engineer, you want to have a look at it. This is how it looks like. 0 to 2000, keep it vertical, then build to 30 degrees, then hold the 30 degrees, then build again to 75 degrees, and you have 10,000 feet, 10,000 feet of 75 degrees. And that part is ERD from 5 to 6. Then you drop it to 30 degrees and hit your target. This is the story, okay? If you see it from the side, you kick off, run your casings, and this tangent, 12¼ sections there, 12¼ section drilling, and then you have a casing, then you drop it 30 degree and hitting the target. So it's just a kind of a story about the well, what it is, before I show you something else. So this is the 3D. You can see it's a sort of live thing. And what it is telling you, on my right-hand side, you have a rig. and you kick off and build, run your casings, hit the target where you need to be, tangent, straight line, 75 degrees up to the next casing point. Then you drop it into the reservoir targets. This is like a kind of story. And this is telling you about, let's say, fly down. If you fly it down, you can see it's drilling on my left-hand side. See the changing numbers. On my left-hand side, if you can see the numbers changing, it is telling you what inclination you are on and how, and you are hitting the targets. So this is like a small animation showing you the process of drilling, actually. And you can see how you are now at 75 degree inclination. This is the one that I would like to model today, which is the long tangent, so 75 degrees, which is currently going, and it's 10,000 feet of it. So once it finishes, and then it has another section, which is 8.5 inch section. When it start to drop, it is 8.5 inch section passing through these targets. Okay, so I'll let it finish and we will probably do something else. Okay, so it's passing the target, now it's dropping. You can see the inclination changing, 35, and at 30 it stopped and it start to hit the target. So it is something that we have it in our system that we will teach our guys how to actually use these fancy tools. You can also put in formation tops. You can change the targets. You can do some geosteering. You can do very fancy thing, and you can get into it in no time because it's fun, it's interactive. So you can actually look at this shape of your well and tell me what is the most challenging part would be. The most challenging could be the long 75 degree tangent, or maybe in the top hole, you're drilling 17.5 inch, building aggressively. As you can see, you are building with 3-degree dogleg, which is quite uncommon. For soft formation, it's something very difficult. So it's something that I want to investigate, this 17.5 inch section. I want to investigate 12.25 long tangent. Let's go for 12.25 long tangent and just see what it is telling me with the BHA I have designed or plan to use. So you can see my model. This is another software application, which is the well engineering application. The one that you just looked at was the directional well planning, trajectory planning design application. I brought in my trajectory into this and pasted and created this design out of my ERD well. Then I wanted to see, for example, what is the minimum flow from 5,000, because I will be drilling from 5,000. I will be drilling from 5,000 to 15,000. That's my tangent. That's the length of my tangent. So I want to make sure that from 5,000 measured depth to 15,000, I have no problem. Nothing is breaking. So looking at this chart is telling me when I'm drilling at the TD of my section, my cuttings will be moving up nicely as long as I keep my flow rate to be 620. However, inside the casing, I will have cutting accumulation. I need to have a flow rate that can clean top to bottom. So my flow rate should be 760 so that all these cuttings will go up, and also it should be above that number. So my cuttings will not be stopping at the casing. When I say at the casing, it's actually I'm referring to this place. This is the place where I am having cutting transportation problem unless I bring my flow rate to be 760. So it's a very strange setup, but very common as well for ERD. So what should I do about it? How can I reduce this requirement? And what can I do to improve it? So looking at my model, I can see, okay, so this is my model. I want to see what kind of drill pipe I'm using, what kind of drill pipe it is. And it is actually the 5-inch drill pipe. And I also want to see what is going on with the other stuff that I have. Let's have a look. let's see what is the drilling situation is going. Look at this one there. This is the complete failure, basically. If you are drilling this well, when it comes to 9,000, it start to breach this pink line. And when I say pink line, it is actually the buckling. The buckling will come. Buckling means you are trying to run in the hole and you are buckling, you're not going anywhere. Okay, let me bring in the shedding. So it is showing the red color now. Let's make it slightly bigger and slightly more bigger. So this is the hook load chart. It's telling me that my ERD well from 5,000 to 15,000 drilling, when I go to 9,000, if my friction factor is very high, then I will not be able to run in the hole. I have to rotate the pipe to get in the hole. Or if my friction factor are quite low, I will still break the limit at 2,000. If it is very, very nice friction factor and you have very low friction factor, still you cannot run beyond 13,500 or so. So this is a failure, basically, because you cannot run in the hole, you cannot nicely make trips. Of course, you can rotate in, but it will take you a lot of rig time. That will cost you a huge amount of money if you are offshore. We need to solve this problem. This is the problem with this design. You're failing it. And secondly, you need to have at least 750 GPM. But how about your limit on the standpipe pressure? Your standpipe pressure limit, suppose, is only 4,000. Okay. So you can only drill to this point. You can only drill to 13,000, as you can see. If your limit is 4,000 on the surface that you can pump with, you are stuck. You cannot drill more than that. That's the like 2 or 3 big failures. And how about the torque? Let's show you the torque and see what do you think about the torque. These are torque. Suppose that that drill pipe you are using is good for 25. So you should be okay for most friction factor. You will be safe. So you don't have a problem with the torque because you have a strong pipe. Okay. How about if we try to solve maybe these problems, like, so let me just take you to the requirement. So you are required to pump this much flow, 750. Can we fix it? Can you fix it to make these cuttings go away? The cuttings should be less here somehow. So you could probably think about clearance. There is a well bore. Well bore has maybe the ID of the casing is too wide. Maybe that's why the cuttings are getting in. If I tighten up my ID of the casing, maybe it will help. Let's say 8. Sorry, let's say 7.5. And maybe run this again. It was 750 before, by the way. So look at this one there. Now you got 720. You have you sort of a little bit start to fix it. Maybe use the tighter casing. Tighter casing so the cuttings will move up quickly because annular geometry is changed now. So you kind of use this design to improve your choice of casings. And if you don't like this one, somebody say, we already have this casing. I want to keep the same casing because I don't want to change the casing. It's thicker and better. Okay, in that case, you say, okay, I will fix something else. Then you can say, maybe I can use maybe a kind of bigger pipe. Maybe I'm using 5-inch pipe. Can I use 5.5 inch maybe? So you can say 5.5 inch, and usually 5.5 inch is actually 2.81. Sorry, it was 4.2 inches usually. Okay, so you say, let's check it if that helps. Okay. So you can run this one, and you can actually fix a lot of issues like this one. For example, if you have these, I have just changed this one. So you can see this is slightly changed. So you can actually use different experiments. The starting point will be, what do you need? You start from there. What you actually limited with? You're limited with torque. You're limited with what? What do you actually can change? So it's a kind of a very long journey. The solution for that one is is actually for using maybe the combination pipe, 5.5 inch and 5.5 inch. It is called tapered string. Okay, I'll stop it here and take you back to maybe our presentation to get some questions. Yes, because we are slightly out of time, but we can still ask few of them.